Okay. Hello everybody, and today we will be talking again about dynamic programming. So we are coming further with dynamic programming. We will consider different problems, and at least we will have I hope I will give you the understanding how to solve dynamic programming when the problems are a little bit more complicated than they are. So yeah. Do you see the marker, or should I use another one, because it seems a little bit
it's nice
whitish. Okay, good. So today we will talk about the following problem named LCS. We start from it. We will talk about more problems, but we'll start from this one, which is longest common subsequence. So what this problem is about? You are given two strings, S and T, and you want to find their longest common subsequence between them. For example, I don't know. I don't know, like this. Buttons and ananas. I don't know what buttons is, but I try to take it more interesting. Or did I succeed? Okay, yeah. So, what is the longest common subsequence between these two lines? Can you tell me? What is the length of the longest common subsequence?
O-A-N?
Not really. This is subsequence, not sequence. It is subsequence. So N-A-N, A-A-N. So the length is 3. So it's not specifically continuous sequence. It can be distributed somewhere. So for example, in this case, we will have AAN and AAN here. So how to solve this problem?
I'm so sorry, maybe I don't understand something, but why don't we include S?
Oh, sorry, yeah. Sorry, it's 4, yeah. It says here, thank you very much. Yeah. S is also here. Yeah, so it is 4. So how to solve this problem? Previously, we talked about dynamic programming, and we think that dynamic programming is kind of shrinking the problem to the smaller ones. The question is here, what is the smaller problem? There. And what is the state? What will be the state of the dynamic programming itself? I think this is the first question. What is the state? And the second, how to use the step function, step for induction. So what do you think are the state of the dynamic programming? So we have two strings, and it seems that the dynamic programming should depend on the strings. So we should have at least two parameters there, one for the first string and one for the second string. So at least it's two parameters, but which parameters it should be? Any ideas?
How we can assign to each letter how many letters correspond to our string. So for ananas it will be, for A it will be 1, for N it will be 0, for A it's still 1, and for N before this is gonna be 2, no? That's strange.
No. We are talking about the state here. Like, what you are talking about is not the state, it is you are trying to solve the problem. Okay, so let me give you the answer. I mean, this is a good guess that we can probably solve this problem greedily, but this is exactly the issue with dynamic programming algorithms and greedy algorithms. Because if you see the problem which is greedy, but you cannot solve it using greedy algorithm, then you should use dynamic programming there. That's the main feature here. So I will say that the state is ij, where I is the prefix of the first string and j is the prefix of the second string. So this is the state. So where how many, like, the dynamic programming ij will return what is the longest common subsequence between the prefix of s of length I and the prefix of second string of length j. So that's it. What should be the step function here? Any ideas? So we have a lots of states. So we have square states. Like, do you remember the turtle from the last time, where we had, like, where to calculate the value for the for the string we should come from up and from the left. So this is kind of the same here. So we want to calculate the answer for ij. From where we can get to their ij.
Also from the top or from the left side?
Yeah, also from the top and from the left. But we need, like, the problem here is that when you come from the top and from left, you don't increase their answer because there is no equal characters there. So we should have one more step. From where it will be.
The left upper square.
Yeah, so it should be from the left upper square. And if they are equal, if the two values for si and tj are equal, then we should come from I minus 1 minus j. So dp ij equals to, oh sorry, not this. Sorry, I should prepare their eraser. Okay. there. So it should be, and it's too wet. Okay. So it should be maximum of dp I minus 1j, dp I j minus 1, and dp I minus 1 j minus 1 plus 1 if si equals to tj. So here is how to calculate our dynamic programming. So we can come from the top, like that nothing is equal, then when nothing is equal, like the answer for the two prefix, either the last character of one string is irrelevant, either another character of their prefix is relevant, or they both relevant if they come from the pair. That's it. That's the whole algorithm. Questions up to that point? Okay. Then let me continue. So that's how we solved the longest common subsequence. Now we will come to another problem, which is Levenshtein distance. So what is Levenshtein distances? We have two strings again, and we can do the following. We can insert character at any position. Like we can insert in the first string, in the second string. We can change the character of one string from A to B, for example. And that's all. Yeah. So we can have three operations on a string: insert a character, remove or insert a character, delete a character, or change the character of the string to another one. The question is, what is the smallest number of different changes we should make to the first string to obtain the second string? So it is solved similar to the longest common subsequence problem. So let's start from the beginning then. What can be the state? Like if you don't understand, so there is like how to get from buttons ananas. You can erase B. You can change N to T to N, and you can insert A here. So like that. So their editor's distance is 3.
Actually, we know what this editor's distance, but maybe so, but we don't understand what is states.
Like,
So we're doing it, but I can grasp it. What do you mean still?
so in dynamic programming, you should solve their. So kind of the answer for the problem is the answer for the state of the dynamic programming. The state can be obtained from other states which are smaller. So, and here is the question, like in the longest common subsequence, we had the state that for which we kind of solved the problem. We had the prefix of the first, the prefix of the second, and their answer for the state was, what is the longest common subsequence between the prefix of I and prefix of j? So in this problem, it is also very similar to this one. So we can take the prefix and the prefix here and ask, what is their smallest number of differences? Like, what is their distance between the prefix of I and prefix of j? So we again in the square state. And we want to calculate the answer for ij. So we kind of calculate the answer from the, like, I don't know, for example, from the left top, like to the bottom, row by row. So what are again their steps between the states? So we have three operations. We have insert, erase, and change. To be honest, it is not different from the longest common subsequence. Like, it is almost the same. The problem is that even they seem dual to each other. So we could save the longest common subsequence and everything should be either inserted or erased, if you think about that. Not exactly like that, but like approximately. So you want to calculate the dynamic programming for the state ij. So we have three operations. So from where we can calculate ij? From which states?
I think what these two operations, erase and change, erase and insert, give us two additional way to come to ij from the bottom and from the right side.
Yeah, let me start here from one. So, like, to be more precise, from the top and from the left. So you want to calculate from the smaller state. So this one is for the insertion, or for deletion, and this one is for insertion. If you come from the top, then you should erase the character, and when you come from the left, you should insert a corresponding character. From where we have, like, from where the change comes.
From the bottom, because we change in I, and it gives us a step back.
From the bottom? No. So again, you have the prefix here, you have the prefix here. So, like, their intuition is here, is what we should do with the last character of both string. So there are three ways. Either you remove the character here, okay? Either you add a character here, like N, or either you change the last character to match them. So it was T here at first, and then like from I here, and we change this character to match them. So here is N. If you match them, from what state are you coming to?
It's the same.
Yeah,
From the right upper.
Yeah, it's the same. So when you match the last character, your answer can come from I minus 1 and J minus 1. So it comes from here again. But there are kind of two different cases here. So from the top and from the left, we always pay 1. Like to add one change, like to insert or remove a character. But if we come from the top left, we have two cases. Which cases are? Like what can happen with these two characters? There are two different versions. So either we should change it or we shouldn't change them. So we have two options. If we should change them, then we have to make +1. But if they are equal, then we shouldn't change them. That is how you get to the, again, you calculate, now you calculate the minimum because you want to understand the minimal value of their Levenshtein distance. So you calculate minimum from dp ij minus 1, dp I minus 1j, and dp I minus 1j minus 1 plus s I not equal to sj. So if they're equal, we add 0. If they're not equal, then we add 1. So this is like the closed form of this. Like, this is very important for you to understand this because this is one of the most used problem in bioinformatics, the Levenshtein distance, because that's how it's named. You take alignment. So you have two DNA strings and you have to align them, and you align them using the Levenshtein distance dynamic programming. Oh, sorry, +1. Yeah. So the difference between the Levenshtein distance and like the difference between alignment and Levenshtein distance is that these ones are not ones but some constant. So to add a new nucleotide there, it costs 1, yes, but to change the nucleotide from one to another costs different value. So it is a little bit more complicated, and sometimes probably it would be better even to change the nucleotide rather than stay the same. So the only question that is left, unfortunately I forgot about that, talking about longest common subsequence, how to restore the answer. How we can restore the answer here. So the answer will be the answer will be, so we have buttons, and we should do like that. So their alignment will be like that. So here is the alignment. So this means that we remove this character. This means that we inserted a new character, and the difference in the character means that we change it. So, and the question is on how to restore, like you're given two strings, you have to restore this thing. So you want to get how two strings are aligned between each other. Like you should be able to do this. We did this with the we did the same thing with the turtle and the grasshopper last time. So we know that the state is ij. So what should we do to restore the answer? So we found the smallest Levenshtein distance, and we want to restore the answer.
Last time we were going backwards.
Yeah, we were going backwards, exactly. So we store with this. We store from ij, from where we come to it. Like we can store either in pairs, like we've got from ij minus 1, or we can store which type of the way we come from. So for example, this come from 2. So you come from from for nm, where n is the length of the first string and m is the length of the second string. And then you just simply check if it is from nm, if it is from the 1, then we should insert character. If we come from 2, then we should remove character. So we should put either like this, or like this here, to the end of the string. And 3, we come from the change. Then we can have here NA. And then if you come from insert, then you come from ij minus 1, here from I minus 1j, and here from I minus 1j minus 1, and continue backwards. So you know, while true, please do this, 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 and do this.
Vitaly, I'm clear with idea of turning backwards,
Okay.
but we save the information about each step in some variable or array which consists of this number 1, 2, 3.
Yeah, so you have this from array. So you have for each state you maintain an array from where you state either the state from which you come or which step you took to come to.
That's clear. Thank you.
Okay. So for example, the second, this means that this was the minimum of these 3 ways. So you store that I came from 2 or I came from I minus 1 and j. So any questions about this? This is very important. So if you don't understand, I will be happy to explain to you. It's not hard. Okay, this of course the same you can do with longest common subsequence. You just understand from where you come, either from the top or from the left or from the top left, and then you restore the longest common subsequence easily. Please be very thoughtful with getting the answer, because you should add this to the front of the string. So the simplest way is to add it like kind of backwards to the end of the string and then reverse it. Okay. The next problem is another problem that comes from the real world. It is like alignment, like let it mean like tag problem. Do you know what tag is?
No.
Have you ever? Have you ever faced it? Because like this is their, it is kind of an, like you write a text and then you compile it using the LaTeX or MikTeX or like anything else, and it creates the PDF.
Yes, we know about it.
With what? Sorry.
Yeah, we know about it.
Ah, you know about it. Okay, good.
Actually, it's just for a second we thought it's an abbreviation for something.
No, it's like tag as it is. So as you found, it is it looks very nice when you compile it, and all the distances between words is very nicely different and like, very good. So what is happening there? You are given words. And you want to align these words on the page. Now this is not a very good marker. So I don't know, for example, you have huge word, then you have small word, then you have again small, like small, and then you have again like the large word, and etc. So how Word works? Like, you know, I'm pretty sure you know what Word is, like Microsoft Office Word. So what it does, it takes each line and simply put their, like by each line, it puts kind of, if you want to align it nicely, fit to the line of the text, it will do like that. It will like take everything that on the line and distribute them along the line evenly. Yeah, but you can see it is not very nice to look at, because, for example, this would be much better if we put this word to the lower. You will have much better situation in this line, while here it will retain the same, like as it is. Specifically for that, LaTeX uses the penalty of the distance between two words. And then here. So, and the penalty is typical that the penalty for the distance d is d cube. Okay, the first thing that you come to mind is that if you stay the words at the same line, then we should distribute their free space evenly between the elements, because they're the cubic form. Like, I mean, the penalty is smaller if you distribute them evenly between all the spaces. This is some mathematical fact which I'm not asking you to prove anywhere. Yeah, but the question is, you're given a bunch of words, you don't know how they're distributed into lines, and you want to distribute them to lines in order that the penalty is the smallest. So we already know that if we put the words in a line, then we know the penalty for these words. So the question is, how to write the algorithm that will find us the best answer for the problem. That's the question where I stop, and you could think a little bit about that. It is pretty reasonable because you know how to shrink the problem to the previous one. So what you're going to understand. So you want to understand what is the state of the problem. This is the first that you have to understand. The second is what are the steps, or how to get from the smaller state to our state.
Firstly, we will define what actions we can do. So it's put on the same line or either put on the second line. Is it?
Yeah, kind of, yeah.
Okay, and now we build sort of a matrix. Word of text from the left side, from the right side, and then we take a step and we choose the best option, calculating the matrix. So either the next action will be put next word on this line or on the second line, and we choose the smallest.
Unfortunately, this is not very easy to do, because when you add, you don't know the state of the string itself at that point, because you add their elements one by one, but you don't know what is the length of all the previous elements if you do like that. If you add by one word, you don't know, like, if your state is just the I, what is dp of I, then you can't add one word because you don't know what are the other words in this line. So you don't know the distance, because distance should be distributed evenly. Does it make sense?
No.
Yes or not?
No.
Doesn't make sense. Okay, so
I was just for my batch of this. I was working with Bellman equation, so I was just trying to put everything in this way, and then I just kind of realized what are you talking about. And just every single time I just switched to something like this.
Okay, I don't know what to say to this sentence. So really you can't do that as you explained, because if you add one word by one word, you don't know the following. You don't know either this state is like that or the state is like that. If you add one word here and you add one word here, you don't know how their previous words are aligned.
No, we can actually remember previous and we can go through all the rest of them. It will not be denied programming.
Yeah, but problem is that probably this wasn't the best way on how to distribute the words. Because, like, for dynamic programming, you can store their answer for it. Yes, you can store the best way. But the problem is that if you can add the word and just update the best way, this is the greedy problem. So you just add one element by one and update the answer. Unfortunately, this problem cannot be solved in a greedy manner. I cannot formally prove it, unfortunately, but like, you can think about that. It needs a little bit more caution here, rather than adding one word by one word. We can add the whole the whole line, the whole last line. We can traverse through all the words that we can put in the last line that you passed. So dpi is we traverse over j here from the right to the left, and dp of I is equal to the minimum over j of the dp of j plus the penalty for j plus 1 I. So you just iterate over your whole last line. So you when to calculate dpi, you want to check what are the words that are going to put on the last line that you had there. And you just traverse through how many words are in the last line. And we know that in the last line will be the words that are the last before I. So we know what are the words will be at the last line. And then we add it to the answer for the first j elements. Is it clear?
No.
Uh, so we compare two situations. One is when the dpj is not.
So your state is what is the best way to put first I words with the smallest penalty. So that's the question. dpi smallest penalty for I words. Then, how our answer looks like? It is some lines with some number of words. We just iterate over all the possibilities how the last line can look like.
Okay, and we calculate the penalty.
Yeah, and we know when you know the number of words and their length, we can calculate the penalty. This is exactly what I'm doing here. So calculate the penalty plus dpj, because dpj is the best way how to distribute the first j words into lines. Like we said, like dpj will be the smallest penalty for first j words. So we iterate over, we check how many words will be in the last line and which are they will be.
So we solve from line by line.
Yeah, we're doing this line by line, yeah. So you can't do this word by word because you don't know exactly how their answer looks like, the previous, but you can do it line by line because your whole algorithm works line by line. You're like the penalty can be split line by line. Thus you can add it like line by line.
Okay, actually, I think I understood. So, and what we are talking about next? What we are solving now after line by line?
We are solving our problem on how to distribute I words, so we will have the smallest penalty. This is kind of can be achieved, like your penalty is calculated line by line, like that, because the penalty, there is no penalty between two lines. Like you don't have kind of penalty between this line and this line. You have the penalty for one line plus the penalty for the second line plus the penalty for the third line, and etc.
Okay, so and the end, but we just sum up all the best penalties.
Yeah, kind of, yeah. So kind of we like if you want to play this as an answer, so you kind of take the last line. So you take this last line, and you know how to distribute all other words, like one, blah 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 blah, j here. You know the best answer for that. And because your penalty does not depend on in between lines, you can do it line by line. So you can add some words at the last line and then check what is their answer for the previous one. Does it make sense right now?
I think so, but why are we talking about dynamic program? Because we remember state for last line and that's it.
Why it is dynamic programming is because we have state. The state is the prefix.
Okay, just the last. So
Yeah,
it's already dynamic programming, like memorization and graphing. It's already.
Yeah. So this is kind of the simplest thing as dynamic programming. Yeah.
So, I believe somebody already in the problem 5 minutes ago.
Yeah, I mean the dynamic programming is everything that you have states and you have their function on how to calculate the answer for the state. So this is dynamic programming. I understand that this problem seems to be like very strange dynamic programming because it has only one state as a prefix, but still, it is still dynamic programming because like you calculate the answer for the prefix. And you know how to recalculate it from their smaller states. So this is the step. Yeah, and of course there is a base where dp0 equals to 0. This is base. And this is state. So, as you can think, this is exactly as induction is in this example, because you kind of calculate exactly for the first I elements. Like this is the step thing is that we traverse over all previous states and recalculate the answer for the new one. So this is like almost like induction here. Standard. Okay. This will not be in their homework, so don't worry if you don't understand that, but like I would like everybody to understand how to solve such problems. What is the time? Okay, we are kind of fine. If you have any questions about this problem, please ask. Like I would like to cover again. like their hardest problem with the dynamic programming is to understand what state is. If you understand what state is, then you can simply then done the step. The step is easier than come up with the state. So we want to kind of understand how to solve the problem for the smaller things. Okay. So if we finish with the tag problem, we will come to other problem, which will be in your homework. So pay a little bit more attention there. The dynamic programming can be like, it is very hard to come up with a state. So we will talk a little bit more about that, and we will take the following problem as an example. Like, this will be then DP on segments. So what is the problem? You're given the string with the brackets, and you want to understand what is the smallest number of brackets you have to remove in order that your bracket will be correct bracket sequence. Yeah, the brackets can be of different forms. The last time we solved not this problem, the last time we checked that the brackets are the correct sequence.
Are you sure there was two problems about it? And the last one we were deleting the minimum amount of brackets to create correct.
Yeah, but the problem is, I think that problem was solved easily because you had only one type of brackets. Now you have several types of brackets. So you have, like, for example, you have squared ones and round ones. So, how the bracket sequence can be represented? So you have the bracket sequence is either it goes like to the smaller sequence but with two round brackets there, either with two square brackets there, or you have as two smaller sequences. So if you know something about grammars, I think Elizaveta should know about that, but like I'm not sure about others. This is the grammar for their correct bracket sequences. So the correct bracket sequence, either it is their sequence with the correct sequence with two good brackets, either it is the correct sequence but with other two brackets, or this is the join of two, like concatenation of two smaller correct bracket sequences. So this together could help you to understand what is the state. You can see that here dp on the segments here. And we know that each correct bracket sequence can be taken from the smaller ones. So what do you think will be the state of the problem? The state, sorry, not of the problem, but the state in the solution, what it will be.
I think it should be the correct sequence with minimal action.
Yeah, but what is the state? Yes, you understand their answer for the problem. Yes, we should make, like, the answer for the problem is to how much update, like the smallest number of updates that we should do to their sequence in order to make it correct bracket. Yes, I agree with you, Konstantin. But what is the state? Right now you found the problem itself.
Maybe it's a subsequence of the wall sequence, which is also correct, and is resulted from minimal actions.
Yeah. Are you sure that subsequence is where it is not in the, like it is not going one by one, it can be with misses there. We have, like, you are almost right. The state is the segment, not subsequence but segment. So the state is from I to j, dpij. What is the smallest number to remove bracket, like number of brackets to remove at Sij. So not for the subsequence, but for their substring itself. So this is the difference between subsequence, is that it is like the part of this whole sequence, but substring is that it is consecutive. So this is substring. Okay, so we want to calculate that. So then we know that each correct bracket sequence can look like that. Like it comes only in three different ways. So how to recalculate the answer from dpij? Not from, how to recalculate dpij through the smaller states.
We can go from the base state plusing the step result, the function, and then that's how we can end up on dpij.
Yeah, that's exactly the question. What is the step?
Step is we're searching for the smallest number of changes.
Yes. Yes.
So we're taking the action that brings us the smallest number of changes, and it's still. But we should know about the rest of the segments, because otherwise we will not finish this way.
Okay, yeah. So like it seems it's not very simple for you, unfortunately. Like in general, I thought that you will come up. So there are two cases then. So you have dpij. From where it will come? Like let's consider only the last example. So you have a correct bracket sequence, and it is the join of concatenation of two bracket sequence. So it is dpij is the minimum of mean by all the j's of dpij plus dpj plus 1. Oh, sorry. No, jk. So we kind of split the problem into two halves. Since we know that the correct bracket sequence can be obtained by concatenation of two bracket sequences, we can split our substring ij to two parts, which will resolve their answer for the left part and the answer for the right part. Okay, this is the first case. What is about the first two of them? So if Si equals to Sj, then we can return here dp I plus 1, j minus 1. And if Si not equal to Sj, then it is either dp I plus 1j or dp I j minus 1. So you kind of either they're both brackets are fine, then we are done, or they're not the same and one of them should be removed from the substring. So it is either we remove the left one or we remove the right one. That's it. So how should you, like, the question is, how should you traverse the dynamic programming itself? So we will traverse it by length of the substring. So we will start for len of the substring from 1 to n, and then we traverse for I from 1 to n. And then we considered j equals to 1 plus len minus 1, and then calculate dpij. So the base for this problem is dpii. And dp, so the base here will be dpii and dpii plus 1. Why I'm traversing by length is that you calculate the step function using their states which has smaller length. So dpik has smaller length than ij, k plus 1j also smaller, I plus 1, j minus 1 has like smaller length by 2, and this one has a smaller length by 1. Questions? Do you have any questions? Like I would like to answer them if you like, or cover the second time if you need this.
So could anyone make the question repeat? What is the function? No? Okay.
Which function?
I thought we only have one function, something with penalty, because we're taking minimum of this function.
Oh, yeah, sorry, plus 1, yeah, thanks. Yeah, I forgot to add plus 1 here. So in this case we either check whether it is concatenation of, like, suppose that we know the answer for dpij, okay? So suppose we know that the answer is like kind of this substring. We don't know it exactly, but we know that it is. There are 3 cases. Either it is the concatenation. If it is a concatenation, then we can ask, we can iterate through all the split points and ask for the left half to be correct bracket sequence and the right half to be correct bracket sequence. Then, if the two I and j are equal, then they're equal and we can ask for the best what we can get from what's inside. And if we throw away one bracket, either the left or to the right, you should pay 1. This is the penalty here. You should pay 1. And to get the answer without one of these brackets. No, not clear.
I think it's just Okay, I think it will not be clear because not everyone just can. I think it's simple, but I don't see the solution. I just can imagine it. I need to write this down.
Okay, I see. So you need more time to understand. Like dynamic programming is one of the from my perspective, is one of the hardest topics, because like you should get the intuition of the dynamic programming problems. You should you kind of should solve more and more problems on dynamic programming to understand how dynamic programming works, because like you should get the intuition on how to get the states of the problem. Unfortunately, we did like if we would have time, then we will be talking about like different problems, like trying to solve them. Probably I will devote one session specifically for that. I'm not sure exactly right now, but probably we'll have one session where you could try to solve the dynamic programming problems on your own. I'm a little bit afraid to do this by giving you the homework, because you can stuck there and it will be much harder for you. So the question that I want to discuss right now. So I think how to restore the answer, it is quite clear. So you will again take array from, which will explain you in what way you come to this state, and then you recover the answer recursively. I want to talk with you about a little bit different problem, or how to write checker for this problem. Since we don't have much time, we have like 10 minutes. Probably you can answer me the following problem.
Sorry, may I ask not very related questions?
Sure.
We here are interested in the whole amount of homeworks, like we will have one after each lection, or?
Yeah, this time there will be 3 problems, I think.
Okay, but just like in the semester, I just don't know why we ask, but still we do. So we have a homework after each lection class.
Yeah, after each lecture, yeah.
Yeah. Okay. So for the last, we will have like 1 week to solve it, correct?
You have like any time, like you should solve these problems until 31st of January. So it's your turn. Sorry?
When do we have an exam?
That's a good question. To be honest, I didn't want to handle an exam, since if you will solve most of the problems, like the problems that are fixed by me that can be solved, like this is exactly what you need to pass the exam. So to solve all the problems.
Yeah, I understand, but I mean that I guess we have exams at the end of December, not January.
You have exams at the end of December.
So it possibly means that we need to solve our homework till the end of December, not January.
Okay, and what is the question then? Okay, you have to solve it.
You just said that we can do it till 31st of December. That is why I asked.
Okay, then 31st of December, like, yeah. But I thought that the exams are in January, so like typically you can finish the homeworks before the January. If you will not finish let me like, you understand that I'm come up with the ranking issue like like right now. So like I think that let's do the following. You will try to solve the problems as they are before the exam, and on the exam, if you haven't solved the problems for some topics, then we will talk a little bit about them. Okay, so this sounds reasonable. So like if you do not pass all their homeworks, then we will talk through all the semester.
Okay, but if the person, for example, resolved not necessary problems, not required, I mean, but just missed one required maybe, but instead solved, well, like much harder problems,
Okay.
I guess, is it a good point and a plus, or?
Probably a good point, yeah. Probably a good point.
Okay.
Yeah, I think so. I'm not exactly sure right now, but like I don't want to harm you as much as like.
I understand, but everyone just wants well to see it very clear. So okay, thank you.
So do we have time still? Yeah, we have still a little bit of time. Okay, so the problem is the following. You're given a string and you want to understand. So you are given two strings, S and T. And the question is whether S is a subsequence of T. So that's the question. It is not about dynamic programming, it's just like short exercise. So you are given two strings and you want to check whether one string is inside another string as a subsequence. Not as a substring, but as a subsequence.
I have an idea with two loops.
Okay, how?
First, we iterate through the subsequence, and inside this loop, we iterate from the whole string and looking for matches of subsequence and the whole sequence. And if we match, we continue. And
again, as far as I understand, not as a substring, but as a subsequence. So like as we thought, like Aba, Saba, this is T, and this is S. So A is a subsequence of this Abba-Tsaba.
Yeah, I mean, we take the first element of subsequence
Okay.
and then iterate through the whole sequence.
Okay.
And if we did not find the match, we return false, and this is our answer. What S is not a subsequence of T. And if we find the match, we go to the next element of subsequence and repeat.
Okay, so the question is, like, as far as I understand, like, you're almost close there, but like, what should you do in this case? So you find C, you have C, you find C, okay, C is here. Then you take B and you find, oh, B is here, or what?
Oh yeah, and we should change the index when we find the match, and continue the next search for the next element from this index.
Yeah, that's correct. But like, what is the complexity will be? So we hadn't talked a lot about complexity this session, but like, what is the complexity of the algorithm?
Len S multiplied by len T.
No. That's the funniest part, that your algorithm, like, you have the following algorithm. For I in 1 len S, for G in start len T, if Si equals Sj, then start equals J and break. So your algorithm is like that, as far as I understand. So you're looping through all the elements of the S, then you loop from the, like, some start identifier, which is 0 at first, till the end of the string, and if you find the, T, here T, and if you find their equal character, you move the start there and break. Am I right? As I understood you right?
Yeah. The complexity will be another.
Yeah, so what is the complexity of this algorithm? So no, I mean the complexity, this O of length S times T is it is kind of right complexity, but it is much bigger than it really is. So I mean, Konstantin, you're right that this is the complexity of the algorithm, because big O means that it is not worse than that. So you're kind of correct, but to be more precise, this is, the complexity is smaller, a little bit tiny. Could someone help Konstantin?
Log len T.
Not log. Okay, next attempt.
In the worst scenario, we will result the half of T string at each step. Is I right?
No, the start can be always the first one, like first letter, second, third, and etc. Like, I would like them to give you a hint. So I is iterated through 1 to len S. Okay. But how much time how much time the J is traversed, like what values J is traversed?
Until it break out from loop.
Yes, until it break out. Yes, that's true. But in total. So you see that you have J here. You come to the place, you break here, but you saved at the start. So the next loop will be starting from the place where it was there already. Okay, I did a small mistake here, so it should be like that. Start plus 1.
It looks like half of T in total. Not sure.
So you are also opting for S logarithm T?
No, S and half of T. That sounds.
So your answer is that, right? S plus T. T over half. You told me here, right? This is your proposal, Elizaveta?
No, I believe it's still multiplication because we have 2 loops.
You still believe that?
It's just
Okay. Don't worry. So we almost don't have time, so I will explain you the mystery here. Or you want to think on your own? That's the question. You want me, so I will give you the answer, or you want to think a little bit and we will talk about this like next time?
The second options.
The second option, okay. So like here is the algorithm. It is pretty simple. It won't take you much time like to understand. So you have this algorithm, so you're passing from like let me write it cleaner here. So you have start equals to -1 here, and here until the length of S, and here until the length of T. Sorry. So you have for E from 1 to S, then for G from start plus 1 to T, and if Si equals to Tj, then we set start equals to J and we break. So here is the algorithm. Okay, let's wait till the next session, or you can try to like, ask me in the chat if you want. I will answer you, of course. Okay, so that's it for today then. Thank you very much for coming, and we will continue with dynamic programming next time.
Thank you.
Thank you.
Bye.
Bye.